Welcome back, Year 10. This is the third lesson, Lesson 3 of Waves. Title today is Reflection and Refraction. So please write down top of page 17, Lesson 3, Reflection, Refraction, and today's date. Before we get started then, let's see where today's lesson fits in with the previous two lessons where we've learned about waves. Lesson 3 then, we are going to be completing pages 17 to 24 in your booklets, and the two parts of the spec or specification telling us what the objectives of this lesson are. And I'll just highlight the parts now we're going to be learning. So we're going to be using diagrams to show plane wavefronts being both reflected and refracted. An example of that are waves in a ripple tank. And in terms of refraction, we'll be learning refraction in terms of the speed of waves on either side of a refracting boundary and the effect on the wavelength of the waves. Top then of page 17, first paragraph. All waves can be reflected. A reflected sound wave is an, so start off at 10. Quick clue, it is an echo, echo, echo. If you've been somewhere for a walk, perhaps near a cliff face, and you've shouted, you might hear the sound of your own voice a few seconds later as that. There's a cliff. There you are. You shout. There's a sound wave. It then hits the wall and comes back towards you. And it could be a few seconds later because sound travels around about 330 to 340 meters per second. So if it came back a second later, that means it's traveled 330 meters. But we're not just looking at reflection of sound waves, we're looking at reflection of light waves and water waves and other waves. So when a straight or a plane wavefront hits a flat barrier, they'd rebound. A little bit like if you play snooker, looking down on top of a snooker table. Okay, there's the pockets, and if the ball hits a cushion, it bounces back off that cushion. Now, that idea of bouncing off or rebounding, we are going to use the word reflect off. The water waves in ripple tank below obey the law of reflection. Now, that part below I've just copied over here so I can make more sense of it for you. You can see, if I draw a line down here, to the right hand side of that line is a simplified diagram of what's the left of the line. To the left of the line is a photograph of water waves, and it's difficult to tell from that photograph that if I just use the ruler to draw a line where the water waves are coming from, so that blue line there shows one of the water waves moving in that direction, and if you follow those lines, you'll see that they will reach a boundary. Now, I've just spent the last couple of minutes drawing in blue the lines that are incident on or about to hit this boundary that I'm going to draw in green. All right, so it hits there. Then what happens is that those waves. They don't change colour. I'm just drawing them like this so that you can identify which waves are reflected, moving away from the boundary, and which one's moving towards. So the ones I'm drawing in red are now moving that way. That way. Okay, so I could continue and keep drawing those red lines in. So if we look over here, these are use a different colour. These ones here are like the blue waves coming in, and these ones here are the reflected wavefronts moving away. So 2 new words: incident rays. Oh, I'll change that highlighter. It's a bit overpowering, isn't it? A bit dark. Incident rays moving towards the barrier, and reflected rays moving away. Incident wave fronts and reflected wave fronts. Make sure you understand the difference between the words rays and wave fronts. The rays are shown by these purple arrows, and the wave fronts are shown by the lines perpendicular to those arrows. So we've got 4 words there. Let's just go through them again. Incident and reflected, rays and wave fronts. Make sure you understand the difference. So the imaginary rays that are drawn at right angles to the wave fronts show the direction of travel. The normal line is imaginary and is at right angles to the barrier. So that's another word we're going to be learning, the normal line. That's this dotted line here, moving up that way. And we use that normal line as a reference point to measure angles. The angle between the incident ray and the normal should be equal to the reflected ray. Now, if I zoom in, and I'm going to pick this middle ray here. Oh, that's the wrong pen to use, isn't it? If I use a ruler and spot for choice with pens, there's the ruler. So if you can imagine that middle ray there coming in, let's give it a different colour. I can't quite get the ruler to do what I wanted to do, so I'm just going to do this from freehand. Not ideal. Comes in there. This angle with the normal here equals the angle here. I'm going to take all the other parts away because that may be confusing the situation. And we call this angle the incident angle and that the reflected angle. So that's what we call the law of reflection. The angle of incidence equals the angle of reflection. So that's what you need to understand first of all. Now what we're going to do is watch a quick video
on that. Everything you can see is bouncing light back at you. Some surfaces bounce light back so well that you can see a reflection. Smooth surfaces like glass, polished metal, and a pool of still water are all good reflectors. Perhaps the best reflector of all is a mirror. Using a mirror, a dancer, and a television camera, we can investigate how light is reflected. Positioned here, the camera can't see the dancer's reflection, but look what happens as the camera moves. The dancer eventually appears. Her reflection is only visible from certain camera positions. Now you see her, now you don't. But why? To work it out, we need to know a bit more about the science of reflection. First, you need a narrow beam of light. Place a mirror in its path and the light changes direction. It's reflected. Change the single beam to 3 parallel beams and see what happens. Light bounces off a mirror.
Okay, now what you saw there was very similar to in your booklet, that diagram here. And what I'd like you to do is draw in those two angles, I and R. I equals angle of incidence. If you've got your protractors on you, I'd want you as well to measure that angle, and R angle of reflection. Okay. So you're going from a real life video there to what's on paper. Hopefully that makes more sense now. And measure, I should say, measure that angle. I haven't got a protractor to hand on here, but what I could do is just use this. If that normal there is at 90, I can't get a reference there, 0, so I have to do 90 take away 51. 90 take away 51 is 39, and I should be getting, if I move it the other way, start at 90 and move it around this way, then I should be getting 51 again. Okay, so it shows that the angle of incidence equals the angle of reflection. It won't be 39 in your box, it'll be slightly different because of the scale.
The ray of light approaching the mirror is called the incident ray. The one leaving the mirror is the reflected ray. Imagine drawing a line at right angles to the mirror where the beam strikes it. The angle between this line and the incident ray is the angle of incidence. The angle between this line and the reflected ray is the angle of reflection. So, what happens when the beam is moved? For each ray of light, the angles of incidence and reflection are always the same size. Light doesn't bounce off the mirror at just any old angle, which is why the dancer's reflection isn't always visible. Rays of light bounce off the dancer in all directions, but only some hit the mirror. Any light hitting the mirror reflects at a certain angle. Stand in this area and the light bouncing off the mirror enters the camera. Stand outside this area and none of the light from the dancer is reflecting towards it. To make the dancer visible, the camera has to move.
Okay, turn over now then to page 18. And it says at the top, when waves such as light or water waves hit a flat surface, we call this reflection. Prediction. When an incident light ray strikes a plane or flat surface, for example a mirror, I think. Your turn now to write down here what you think is going to happen. Press pause, then press play when you've filled in your answer. Now, you should have had something similar to when an incident light ray strikes a plane or flat surface. I think the reflected ray will reflect at an angle equal to the incident ray, at an angle equal to the, running out of a bit of space, incident ray. Okay, the reflected ray will reflect at an angle equal to the incident ray. And you can see that there. When you're in class, you'll be given a reflection handout to reinforce that. Now, your job is to complete the reflected wave after it strikes the flat barrier. And so this is something for you to do now. Please, again, press pause, and when you complete it, press play. Make sure that you draw in the normal line at the point where the incident ray hits the plane barrier. Okay, that's just a helping hand for you. The success criteria on the side here, something I want you to use to make sure you've done everything. Draw in the normal line done, reflected ray, and label the reflected ray. Reflected wavefronts, measure and record the angle of incidence and the angle of reflection, which I'd want you to write in here, please. Right, when we've completed that, we're now going to look at an example, or an application, I should say, of mirrors. Periscopes. Periscopes are used for looking over things, almost giving yourself that extra height advantage, or looking at being able to look around corners. Perhaps is another way of explaining the uses. It can be used perhaps if you're in a large gathering, like a sports ground and watching a game of football or rugby, and you want to see over the top of someone. Used in battle. Used the First World War, looking over the trenches, and that's why you've got a soldier just here. So what you need to do is show how this array of light, which is being reflected off this soldier and gets into this person's eye. So this could be someone, I'll do that in red. That could be someone then who's trying to hide from that soldier, and he wants to know where the soldier is. So using this periscope, he's able to see him, And what you need to do is, should really start from the top like that, and then draw the reflected rays. They should all match up. It's important to show the direction that the light is travelling. It's going from the soldier to the eye. Underneath, in your own words, two things here. Explain what periscopes can be used for and how they work. So, what can periscopes be used for and how do they work? How do they work? So an application, at least one application of a periscope, please. So that's pretty much it for reflection. Just before we move on to refraction, this is just a piece of software that's available on a website. And you can see by moving the ray box around here, if I've got 70 degrees, which is the angle of incidence. If I move the cursor from there to there, you can see that's 70. That's your angle of incidence. And your angle of reflection is that there. So you can go on school website and do that yourself. Don't mix up refraction with reflection. They sound very similar, but look at the spelling. And it's not faction, it's fraction. What is it? It's when water waves, or any waves actually, travel from deep water into shallow water. It's when waves change direction when they go from one medium to another. This is just an example, water waves. They slow down and the wavefronts get closer together. We learned about this actually when waves break near the shore. That when you've got waves, they get near the shore, the back of the wave catches up with the front because it's in deeper water, so the wave breaks. Now, when this happens and the change in the speed is at an angle, it causes like we've got here, it causes a change of direction. And the change of the direction is all to do with a change in speed.
Light travels in straight lines. Shining a powerful light source through a thin slit produces a straight, narrow beam. Place a glass block in its path and the beam starts to behave differently as the block is rotated. Some of the light is reflected, the rest passes into the glass. The light bends in one direction as it enters the block and in the other as it emerges from the lower edge. This shift in direction
Refraction of light waves. And the reason the light is refracting is because it's going from air into glass. Light travels more slowly in glass, therefore it changes direction. It's exactly the same as we just saw with water waves.
Is called refraction. To work out what's happening, think of light as a series of waves. This ripple tank uses a dipper to send parallel water waves across its surface. Putting a plastic sheet into the water makes this part of the tank shallower than the rest. Waves travel more slowly in shallow water. This change in speed changes the wavelength. The wavelength on the top is shorter than the one on the bottom. When the sheet is at an angle, the waves also change direction. The wave fronts bend as they reach the plastic sheet. To understand how speed can cause a change of direction, imagine a truck approaching marshy ground. If the marsh is at an angle, the right wheel slows first. The left carries on at speed for longer, swinging the truck round. So when light hits a glass block, it changes direction because it changes speed. Place a glass trough in the beam, and you can see how water also affects the path of light. The bending of light helps explain why this apparently straight stick is in fact bent. While this bent stick is actually straight. Refraction tricks our eyes, making us think that the stick is nearer the surface than it actually is. These are diving for their underwater prey.
Okay, now having watched that video, what you need to do is here, in your own words, finish off the sentence and add some more detail. As a wave moves from deep into shallow water, you've got to explain what happens next. So I'll give a type of verbal answer, and then you can put it in your own words. So when the wave moves from the deep into shallow water, the waves slow down, and as the waves hit a boundary at an angle, the waves change direction. The wavelength of the waves also decreases. Okay, so what you need to include, you've got to say that there's a change of direction that's called refraction. You've got to say why that happens, and it's because the water slows down. Now one thing, so complete that and then press play when you've completed your answer at the bottom of page 20. If we look at this example now underneath, it says light travels faster through air. Air is less dense. Light travels more slowly through glass. We saw that in the video, which is a medium, denser than air. And you can see that happening there. Fast here in the air, slow in the glass, and fast again there. Now, that is shown again in two different ways underneath here. And what you need to remember is that when the light goes from the air into glass here, it bends towards the normal, and here it bends away from the normal. There isn't a normal drawn on there. I'll add one in. The normal should go here. I'll use a different colour. So there's a normal line there. Bends towards a normal on when it slows down, and away from a normal when it speeds up and it goes back into the air. When you're in class, you're going to do that experiment and you're going to stick your A4 sheet of your refracted rays just there. So before you do that experiment though, I'm just going to show you another simulation of refraction. Now if you look at this, we can move the laser back and forth. You can see there's a refracted ray. There's a bit of reflection happening there, but we're more interested in this refraction, and you can see it's bending there towards the normal. And we can use a protractor there to measure the angle of incidence. Looks to be about, what's that? That's going to be about 75, and the angle of refraction is 45. Now we can show the wavefronts. So those are the wavefronts, and that's the ray. So you now when you've done the experiment, you stick that sheet there. And it's time for you to do some questions on today's lesson. If you look at this first one, this is a self-assess question. So I'll just put asterisks now next to what you need to do. 22. And when you've completed that question, press play. Okay, you can mark this with a red pen yourself or correct with a red pen. The first one, I hope you all got this one. State the name of this effect, that's refraction. Tick 2 boxes, the correct statements. Well, it's the wave speed is less in shallow water and the wavelength decreases in shallow water. Part C, a wave's got a wavelength of 7 centimeters and frequency of 6 Hz. Use an equation to calculate the wave speed. Well, we've used this equation before. Speed is frequency times wavelength. Notice here it's asking for the answer in centimeters per second. So it's okay on this occasion to write down the wavelength in centimeters. Almost always in physics we work in meters, but on this occasion it's fine. 7 6s, 6 7s, as 42. And that is now not meters per second, but centimeters per second. Turning then on to page 23, it says the material that a wave travels through is called a medium. Light can travel through several. So let's just list a few. Air, glass, perspex, and water. As waves enter a different medium, the speed of wavelength changes, and this causes them to change direction. We know this is called refraction. So this is a bit of a recap, really. If the wave slows down, air to glass, it bends towards the normal. If the wave speeds up, it bends away from the normal, or refracts away from the normal. I showed you that a few moments ago. It's happening here. It's refracting away, further away from that normal. And here, when it slows down, it's towards, it goes that way, towards the normal. Overdid that. Zoom function, overcooked it. Right, homework. HW. So to just finish off this lesson, let's quickly look at those homework questions. Questions 1, 2, 3, 4, 5, 6 and 7. You'll notice on the very last question here, it's asking you to calculate the frequency and to use the equation sheet, which you'll find in the inside front cover of your booklets. So that's the end of this lesson. See you next time. Bye.